Welcome to the deep dive. Today, we're doing something a little audacious. We're sort of taking a massive intellectual shortcut.
We
We're
are.
not tracing the history of quantum mechanics with all its confusing detours.
hmm
We're jumping straight to the deepest, most fundamental principles, the ones that really dictate how subatomic particles behave.
That's right. Our source material here argues, and I think it's a great point, that to truly get the quantum world,
Hmm.
you shouldn't start with the historical struggle or these complex wave equations.
Right.
You should start with the one core concept that just fundamentally replaces everything we know from classical reality, and that's the probability amplitude.
So our mission today is to internalize that,
Mhm.
to get the language. We all understand classical probability, the likelihood of a coin flip or a die roll.
Mhm.
But in the quantum world, that whole idea of likelihood, it doesn't even enter the picture until the absolute last step.
Exactly. The central non-negotiable shift is that classical probability is just. It's gone. It's replaced by this complex thing called the probability amplitude. Think of it as the fundamental currency of quantum mechanics. It's a complex number, which is key. The actual measurable probability of something happening only emerges when you take this amplitude and multiply it by its complex conjugate.
Which is the technical way of saying you take its absolute square.
It is, yeah. That's the only way to get a real number, a real probability out of it.
I want to focus on that word complex. Why can't it just be a normal real number,
Yeah.
like classical probability? What is complex by us?
Well, because a simple number only tells you the magnitude, how big the likelihood is. A complex number, importantly, it carries phase information.
Okay.
You can almost visualize it like a little vector or an arrow. It has a length, which is the magnitude, but it also has a direction, a phase. And this ability to carry phase is the mechanism that allows for interference.
Ah.
If two amplitudes come together, their little arrows can add up if their phases align, or they can entirely cancel each other out if they're pointing in opposite directions, just like waves on a pond.
So the complexity of the amplitude is the secret sauce. That's what allows things to interfere in this totally non-classical way.
Hmm.
If it were a real number, we just have boring old probability.
You just have coin flips, yeah?
No interference.
Okay, that distinction is crucial. So let's move to the two fundamental rules for how we handle these amplitudes, the non-negotiable laws.
And they're surprisingly simple, conceptually.
Hmm.
But they lead to, well, all the weirdness we observe.
Let's start with the first one. This is, for me, the most counterintuitive principle when you stack it up against anything in our big macroscopic world.
It has to be. This is the first general principle, and it deals with alternative routes. The rule is this. If a quantum event can happen in several different ways, and this is the critical part, these ways are physically indistinguishable, meaning there's absolutely no way, even in principle, to tell which path was taken.
Okay.
Then the total probability amplitude for the event is the sum of the amplitudes for each of those alternative ways. So if a particle can go via path A or path B, and we genuinely have zero information about which path it took, we have to add the complex amplitude for A and the complex amplitude for B.
Precisely. You add them first, and only after that summation do you square the result to get the final probability.
And that's where interference comes from.
That's it. Because you added those amplitudes, which remember have a phase, they're like little arrows. Before you squared them, you get these cross terms in the math. Those cross terms are quantum interference.
Whereas in classical physics, if a ball could take two routes, you just calculate the probability of route A, then the probability of route B, and just add those two numbers together at the end.
Right, you'd sum the final probabilities.
But quantum mechanics says, no, the probability of the total outcome comes from the sum of the possibilities.
The order of operations, sum before you square, is the whole game.
Okay, now for the second rule. What happens when it's not alternatives, but steps in a sequence?
That's the second general principle for successive events. If an event is a sequence, say, a particle goes from state S to an intermediate point B, and then from B to a final position F.
A to B to C.
Exactly. The amplitude for that whole journey is just the product of the amplitudes for the separate steps. You multiply them.
So if the amplitude for step 1 is phi1 and the amplitude for step 2 is phi2, the whole sequence is just phi1 times phi2.
It's that simple. Multiplication for a sequence, addition for alternatives.
And the book introduces this clean shorthand for this.
Right.
The bracket notation.
Yeah, the angle brackets. It's just a way to write the amplitude for going from start to finish. It keeps the math from getting out of hand when you have these long chains of multiplication and addition, which, that's what every quantum process is.
Okay, let's apply that first principle, the summing of alternatives, to the most famous thought experiment in physics, the two-slit experiment. This is where the system really shows its philosophical teeth.
Absolutely. So you have an electron gun. It's firing particles at a wall with the two tiny slits, slit 1 and slit 2. And behind that wall is a detector screen.
Right.
If we do nothing to monitor the electrons, if we just let them go, they pass through both slits at once, so to speak. The two paths are indistinguishable alternatives.
So the particle takes the amplitude for going through slit 1, adds the amplitude for going through slit 2, and that summation is what creates that classic wave pattern on the screen, the interference.
But here's the pivot. This is what shows you the true nature of these rules. What happens if we decide we want to know the path?
We get greedy for information.
We get greedy. Say we put a little light source and some detectors near the slits, and we see a photon scatter off an electron right behind slit 1.
We've just introduced knowledge into the system. We've made the alternatives distinguishable.
And the second we gain that knowledge, the interference pattern completely vanishes. Gone. The distribution on the screen just collapses to this boring classical result. Just two clumps, one behind each slit.
Why? Why does the rule change? I mean, that's the central mystery, isn't it? Is the particle somehow sensing our observation?
It feels like that, but the source is very clear. It's not about being watched. The rule change is forced because the act of measurement itself creates a new distinguishable final state.
Oh, I see.
When we look, we're not just asking, did the electron land at point X anymore? We're now asking a more complex question. We're asking, did the electron land at point X and a photon get detected at our little detector D1?
Or did the electron land at X and the photon get detected at detector D2?
Exactly. The total final state of the entire system, the electron plus our detector, is now different for the two alternatives.
Ah, so because the final outcomes for the whole system are now distinguishable, you can tell them apart by looking at which detector lit up. The rule forces us to switch.
You got it. We now have to sum the final probabilities for these two separate total outcomes instead of summing the amplitudes first. And when you do that, all those beautiful interference cross terms just disappear.
The cost of knowing the path is the destruction of the interference.
It's the highest stakes information trade-off you can imagine. You get the which way data, but you lose the wave nature completely.
Let's scale this up then. Let's go from two simple slits to millions of possibilities, like neutrons scattering from a crystal.
Right. So we replace the wall with two slits with this highly ordered periodic array of nuclei in a crystal lattice.
Okay.
When a neutron beam hits that crystal, the neutron can scatter off any single nucleus in that structure. And since scattering off nucleus 1 is indistinguishable from scattering off nucleus 10,000, we don't know which specific atom it hit.
The rule applies. We have to sum the amplitude.
We have to sum the amplitudes for scattering off every single nucleus in that crystal.
And when you sum millions of tiny amplitudes, all with slightly different phases, you get a very sharp, distinct interference pattern. We call it diffraction. And that pattern actually tells you the structure of the crystal.
Exactly. But now let's add another layer of complexity that's often overlooked. Spin. Neutrons and the nuclei they scatter from have this internal quantum property called spin. You can just think of it as being in one of two states, up or down.
So the scattering isn't just about position anymore. It involves the internal state of these particles. The interaction could cause the neutron's spin to flip from up to down, for instance.
Exactly. Which creates new alternatives for the final state. Say a neutron starts with its spin pointing up. After it scatters, the alternatives could be the neutron's spin stays up or the neutron's spin flips down.
And this brings us right back to distinguishability, but now it's based on an internal property, not a physical path.
Precisely.
So if we don't measure the final spin of the neutron, we just count all the neutrons that hit our detector, then the alternatives are indistinguishable.
Correct. The final state neutron spin up gets grouped with the final state neutron spin down. They're both just a neutron hit the detector. So we sum the amplitudes for those outcomes, and we get to keep our sharp interference peaks.
But if we're clever, and we put a spin analyzer on our detector, something that only counts neutrons with spin up, for example, we've gained specific knowledge about the internal state.
And then the alternatives become distinguishable. The act of measuring the spin separates the outcomes, and it forces us to switch the rule again.
So we have to sum the probabilities for this separate spin result.
We do, and when you sum probabilities instead of amplitudes, that sharp interference pattern gets washed out. It's replaced by a smooth, broad distribution. The quantum rule is absolute. Knowledge, in any form, dictates the math you have to use.
It doesn't care what information we get, position, momentum, Spin only that we got it.
That is the whole lesson.
Okay, now we move to what might be the most profound part of this whole thing. The problem of identical particles. This goes beyond just position and spin. This gets to the fundamental nature of matter itself.
This is where a new, really astonishing rule just emerges from the math. First, let's think about two distinguishable particles scattering. Say, an alpha particle hitting an oxygen nucleus.
Okay, two different things.
Two different things. If we put a detector at a certain angle and it clicks, we know two things could have happened. Either the incident alpha particle scattered to that angle, or the oxygen nucleus it hit got knocked forward and ended up in the detector. Since they're different particles, these two final possibilities are distinguishable.
So we use the classical like rule. We find the probability of the first event, find the probability of the second event, and we just add those two final probabilities together. We sum the squares.
Exactly, no interference. But now, let's consider two identical particles, one electron scattering off another electron, and let's say their spins are aligned so they're truly identical.
Okay.
Because the electrons are fundamentally identical, the two scattering routes, electron 1 scattering to our detector versus electron 2 scattering to our detector, are completely indistinguishable alternatives.
Which means the principle of summing amplitudes has to apply.
It has to. This gives us what's called exchange interference.
So we sum the amplitudes. But the source points out a critical new rule of nature here, something that fundamentally changes the math with a sign.
This is the truly remarkable part. For electrons, which belong to a class of particles called fermions nature just, mandates that the exchange interference term, the bit of math relating the two indistinguishable paths, it has to carry a negative sign.
A negative sign? Wait, so instead of adding the two amplitudes together before squaring, we're actually forced to subtract one from the other.
That's it, exactly. The resulting probability involves subtracting the amplitudes. The amplitude for the direct scatter minus the amplitude for the exchange scatter. This subtraction creates an interference pattern that's profoundly different from the additive interference we saw with the two slits.
Wow.
And it's different from the positive sign you'd use for other particles called bosons. It is a fundamental new requirement of nature for identical particles like electrons.
That's incredible. The difference between adding two little arrows and subtracting them is a tiny sign change in an abstract equation, but it dictates a universal truth about matter.
It's the ultimate example of how the laws of nature are written in this language of amplitudes.
Okay, let's unpack this for a second. We've dived into the core of quantum mechanics and established that events are governed by these complex probability amplitudes, not classical probabilities. The rules are absolute.
Right. We've basically established that the whole structure rests on 5 key pillars just from this one chapter.
First, the fundamental thing is the amplitude. It's a complex number with a phase, and you have to square it to get a measurable probability.
Second, indistinguishable routes demand you sum those amplitudes, and that's the machine that generates all interference effects.
Third, successive events in a chain mean you multiply their amplitudes.
Fourth, the act of determining the path, even just getting information about spin, collapses the system. It forces you to sum the final probabilities instead. Knowledge literally destroys the superposition.
And finally, identical particles introduce exchange interference, which, for particles like electrons, requires that crucial enforced negative sign. You subtract the amplitudes.
And if you connect this to the bigger picture, the sheer rigidity of that rule, that you must sum amplitudes whenever you cannot know the path, it suggests reality at the quantum level is just, defined by this superposition until an observation forces a collapse. It raises that question: what does it mean that reality is defined not by what is, but by what is fundamentally unknowable?
Wow.
And here's a provocative thought for you to chew on. That mandatory negative interference sign for fermions, the one that forces you to subtract the amplitudes for 2 electrons. That is the physical, mechanical foundation of the Pauli exclusion principle. That tiny minus sign is the reason 2 electrons can never occupy the exact same quantum state. So consider this. That tiny mathematical sign difference governs the stability of atoms, the structure of the entire periodic table, and literally all of chemistry as we know it.